Right now, as you watch this, two human-made objects are drifting through interstellar space, carrying a gold-plated record with greetings in 55 languages. The sound of a human heartbeat and music. A message in a bottle hurled into the cosmic ocean, meant for whoever or whatever finds it in a billion years. At the same time, giant dishes scattered across the Earth are pointed at the silent stars, straining to catch a single artificial whisper from someone out there. And invisibly, expanding in a bubble around our planet at the speed of light, are decades of our radio and television broadcasts, already washing over thousands of nearby stars. We have been trying to talk to aliens for over 60 years. We've shouted, we've whispered, we've sent physical artifacts, we've listened with the most sensitive instruments ever built. And so far, total silence. But the methods we've dreamed up to bridge that silence are some of the most ingenious, strange, and quietly beautiful ideas our species has ever had. Today we're going through all of them. Every way humanity has tried, or could one day try, to make contact. From a golden record on a 1970s spacecraft, to lasers brighter than the sun, to messages written in neutrinos and gravitational waves. This is the complete toolkit for talking to the universe. Let's start by splitting the problem in two, because communicating with aliens is really two opposite tasks. One is listening, pointing instruments at the sky and hoping to detect a signal someone else sent. The other is talking, actively sending our own message outward. Scientists call the listening side SETI, the search for extraterrestrial intelligence, and the talking side METI, messaging extraterrestrial intelligence. Almost everything humanity has done falls into one of these two buckets, and as we'll see at the very end, the question of whether we should be doing the second one at all is one of the most heated debates in all of science. But first, the methods themselves. And the oldest, simplest one isn't a radio signal at all. It's a physical object. Think about how humans have always sent messages across impossible distances. A note in a bottle, a letter, a time capsule buried in the ground. The most poetic attempts to contact aliens are exactly that. Physical artifacts, launched into space, carrying a message etched onto them, drifting forever in the hope that someone eventually picks them up. The first of these flew in the early 1970s aboard two spacecraft called Pioneer 10 and Pioneer 11. Each carried a small gold-anodized aluminum plaque, engraved with a simple drawing. Two human figures, a man and a woman. A map showing where our sun sits relative to a set of pulsars, and a diagram of the hydrogen atom to establish a basic unit of measurement. It was, essentially, a cosmic "we were here" scratched onto metal. The idea was that any civilization advanced enough to catch the probe could, in principle, decode where it came from and who built it. That pulsar map deserves a closer look, because it's a genuine stroke of genius. A way to write down a cosmic return address. Pulsars are the dense, rapidly spinning corpses of dead stars, and each one flashes with its own extremely precise, unique rhythm, like a lighthouse with a distinct heartbeat. The plaque marked the position of our sun relative to 14 of these pulsars, encoding each pulsar's exact flash rate in binary. Here's the clever part. Those flash rates slowly change over time in a predictable way. So an alien who found the probe could, by checking which pulsars match those specific rhythms and how much they drifted, figure out not only where in the galaxy the probe came from, but roughly when it was launched. It's a map in both space and time, written in a language any astronomer in the galaxy could read, because pulsars are visible to everyone. The same pulsar map was later etched onto the cover of the Voyager Golden Record. In a very real sense, we've already mailed our home address to the stars, which, depending on your view, is either a beautiful act of cosmic openness or a reckless one. Then, in 1977, came the masterpiece. The two Voyager spacecraft each carried what's now legendary, the Golden Record, a 12-inch gold-plated copper phonograph disc, along with a stylus and instructions for playing it, etched into the cover. And what's on it is breathtaking. Greetings spoken in 55 languages, from ancient Akkadian to modern dialects. The sounds of Earth, thunder, wind, rain, birds, whales, 90 minutes of music spanning cultures and centuries. and a series of encoded images showing our planet, our biology, our cities. It was conceived by a team led by Carl Sagan as a portrait of humanity at its best. No war, no suffering, just a snapshot of a living world saying hello. The beauty of these physical messages is that, unlike a radio signal, they don't fade. A radio wave passes a star in an instant and is gone forever, growing weaker as it spreads. But the golden record is a permanent artifact. It will outlast the Earth itself. Long after our sun has died, those records will still be drifting through the galaxy, essentially intact, because in the vacuum of space, there's almost nothing to erode them. The catch, of course, is staggering. Space is unimaginably empty. The probes are tiny and not aimed at any particular star, and the chance of one ever being found is almost vanishingly small. Voyager won't even come close to another star for tens of thousands of years. These messages are less a practical phone call and more a gesture, a bottle thrown into an ocean so vast we may never know if it washes ashore. But the gesture matters. It says, we existed and we reached out. Now, if physical objects are impossibly slow, there's a far faster courier, one that travels at the absolute speed limit of the universe: light, radio waves. And this is where the real, serious effort to contact aliens lives. But before we even get to the messages we sent on purpose, here's an unsettling fact. We've been broadcasting to the stars by accident for about a century, and we can't stop. Every radio transmission, every television broadcast, every powerful radar pulse leaks some of its energy out into space. Since the early 20th century, this leakage has been expanding outward from Earth in a growing bubble, traveling at the speed of light in all directions. That bubble is now over 100 light-years across, meaning the earliest broadcasts have already washed silently over thousands of nearby star systems. If any of those systems holds a civilization with a sensitive enough receiver, they may already know we're here, not from a deliberate message, but from the faint electromagnetic murmur of our daily lives. This matters enormously for the whole debate, because it means the question, should we reveal ourselves, may already be moot. The horse, to some extent, has left the barn. Though it's worth noting, these leaked signals are weak and scrambled, fading into noise over distance. So a deliberate, focused broadcast is still vastly louder than our accidental chatter. Still, the idea that Earth has been quietly announcing itself for 100 years, whether we meant to or not, reframes everything that follows. The logic of deliberate radio is simple and powerful. Radio waves travel at the speed of light. They're cheap to produce, and they can pierce straight through the gas and dust of space that would block ordinary light. So if you wanted to deliberately announce your existence to the galaxy, a powerful radio broadcast is the obvious tool. And in 1974, humanity did exactly that, in its most famous deliberate transmission ever, the Arecibo message. Using the enormous Arecibo radio telescope in Puerto Rico, scientists led by Frank Drake beamed a short, intense radio message toward a dense cluster of stars called M13. The message was a piece of pure cleverness. It was just over 1,000 binary digits, ones and zeros, and the number was deliberately chosen because it's the product of two prime numbers. The hope was that any mathematically literate alien would realize the only sensible way to arrange those digits is into a grid of a specific width and height, turning the stream of bits into a picture. And when you do arrange it correctly, you get a series of crude images: the numbers 1 through 10, the chemical elements of life, the structure of DNA, a stick figure of a human, our solar system with the third planet nudged toward the viewer, and a picture of the telescope itself. The whole thing was a demonstration, proof that we could do it, more than a serious attempt at conversation, since that star cluster is 25,000 light-years away, meaning any reply couldn't arrive for 50,000 years. Other radio messages followed over the decades. Projects with names like Cosmic Call beamed toward nearby sun-like stars from a radio telescope in Crimea, carrying updated encyclopedias of human knowledge. And the impulse to compose the perfect message hasn't faded. If anything, it's grown more sophisticated. In recent years, scientists have drafted modernized successors to the Arecibo message. One proposal, called A Beacon in the Galaxy, lays out a detailed binary message designed to be broadcast toward the dense star fields near the center of our galaxy, updating the 1974 message with our location, our biochemistry, and an invitation to respond. Another effort, Message in a Bottle, reimagines the golden record for the digital age, debating what humanity should choose to say about itself now, how to portray our science, our art, our existence, with decades more wisdom about the problem. These projects wrestle with genuinely hard questions that the original messages glossed over. What do you include? Do you show our flaws or only our triumphs? Do you reveal our exact location or stay vague for safety? How do you compress the entirety of human civilization into something an alien mind, shaped by a wholly different evolution, could possibly unpack? Every attempt to write a message to the stars turns out to be, secretly, an attempt to define who we are, which is perhaps why these messages say more to us than they ever will to anyone out there. But here's the thing. Shouting is the rare exception. Overwhelmingly, humanity's effort has gone the other way, into listening, into SETI, because most scientists figure it's smarter and safer to quietly eavesdrop on the galaxy than to announce ourselves. And the modern search for alien signals began with one man and one telescope in 1960. His name was Frank Drake, the same Drake behind the Arecibo message, and his experiment was called Project Ozma. He pointed a radio dish in West Virginia at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and simply listened for any artificial signal. He heard nothing alien, but he started a field. A year later, Drake wrote down what's now called the Drake equation, not really a formula to solve, but a way to organize our ignorance. It strings together the factors that would determine how many communicating civilizations might exist in our galaxy. How many stars have planets? How many of those planets could host life? How often life becomes intelligent? How long a civilization survives and keeps broadcasting? Plug in optimistic numbers, and the galaxy should be teeming with signals. Plug in pessimistic ones, and we might be utterly alone. The honest truth is we don't know most of those numbers, and the equation's real value is in showing us exactly what we don't know. But Drake's experiment raised an immediate, maddening question. If you're going to listen, what frequency do you tune to? The radio spectrum is almost infinite. Searching every possible channel is like trying to find one specific radio station when the dial has billions of positions. Scientists needed a natural frequency, one that any intelligent species across the galaxy might independently think of as the obvious place to broadcast. And they found a gorgeous answer. Throughout the universe, hydrogen, the most common element, naturally emits radio waves at a specific frequency, near 1,420 megahertz. Any civilization doing radio astronomy would know this frequency cold because hydrogen is everywhere. Even better, right near it sits the emission frequency of another molecule, hydroxyl. Together, hydrogen and hydroxyl combine to form water, the molecule we think life needs. So scientists poetically named this band of frequencies the water hole, a watering hole where, like animals on a savanna, different species might gather to meet. For decades, it's been the favored place on the dial to listen. And then, just once, the listening seemed to pay off. On August 15, 1977, a radio telescope in Ohio, nicknamed Big Ear, was scanning the sky when it caught something extraordinary. A powerful, narrow signal right near that hydrogen frequency that rose and fell over 72 seconds exactly as you'd expect from a fixed point in space, passing through the telescope's view. It was so strong and so unlike any natural source that the astronomer reviewing the printout circled the data and scrawled a single word beside it. Wow. The wow signal, as it's been known ever since, remains the most tantalizing candidate ever detected. It had the hallmarks of an artificial transmission. And here's the maddening part. Despite countless attempts over the decades, it has never been heard again. One burst, 72 seconds, and then eternal silence. We still don't know what it was. The wow signal isn't the only cosmic mystery that set off alien speculation. In more recent years, astronomers discovered a baffling new phenomenon: fast radio bursts, incredibly powerful flashes of radio energy, lasting just milliseconds, arriving from billions of light years away, each releasing in a fraction of a second as much energy as the sun pours out in days. When they were first found, Their sheer power and strangeness led a few researchers to at least raise the question of whether they could be artificial. Perhaps the leakage from Titanic alien engines or beams powering interstellar spacecraft. As more were detected and studied, natural explanations gained ground, most pointing to extreme dead stars called magnetars. But the episode is a perfect illustration of how SETI actually works in practice. Whenever the universe shows us something powerful and unexplained, could it be a civilization? Is a question scientists genuinely have to consider and then rule out. The history of astronomy is full of these moments. Even the very first pulsars discovered in the 1960s were jokingly labeled LGM for little green men, before their natural origin was understood. Each time, nature has turned out to be the answer. So far. Today, the listening effort is bigger and more powerful than ever. The flagship is a project called Breakthrough Listen. Launched in 2015 with $100 million of funding, the most comprehensive SETI search in history. It uses some of the world's largest radio telescopes to scan over 1 million nearby stars, listening across billions of channels at once, each just a few hertz wide. A feat utterly impossible in Drake's day. There have been heart-stopping moments. A few years ago, the team found a candidate signal called BLC-1 that appeared to come from the direction of Proxima Centauri, the very nearest star to our sun. It was a pure tone, narrow, and it drifted in frequency the way you'd expect from a transmitter on a moving planet. For a while, it looked genuinely promising. In the end, it turned out to be interference from human technology back on Earth. A sobering reminder that we live in an ocean of our own radio noise, which makes finding a faint alien whisper desperately hard. SETI has also famously enlisted the public. A project called SETI at Home let millions of ordinary people donate their home computers' idle time to sift through telescope data, hunting for the needle in the cosmic haystack. It's worth appreciating the sheer machinery now aimed at this question, because the instruments are staggering. There's a dedicated array of radio dishes built specifically for SETI, able to listen to many star systems at once, watching the sky around the clock. There's the largest single radio dish ever built, a 500-meter giant nestled in a natural bowl in the landscape, sensitive enough to catch almost impossibly faint whispers. There are the great 100-meter dishes that can be steered to point at any target astronomers choose. And increasingly, the search piggybacks on other telescopes, quietly analyzing the data they gather for other purposes, squeezing a SETI search out of observations made for ordinary astronomy. The total listening power humanity now brings to bear dwarfs anything Frank Drake had in 1960 by factors of millions. And yet, the sky stays silent, which forces an uncomfortable thought. Either no one is broadcasting in a way we can hear, or we're still somehow not looking in the right place, at the right frequency, at the right time. Searching the whole sky across all frequencies continuously is a task so vast that even after 60 years, we've barely sampled a teaspoon of the cosmic ocean. But suppose we did catch a real signal. That raises a problem we've been quietly stepping around. Maybe the deepest one of all. How would we ever understand it? We share no language, no history, no biology with an alien civilization. How do you decode a message from a mind shaped on another world? The answer most scientists land on is the one thing we might truly share with any technological species: mathematics. The laws of math and physics are the same everywhere in the universe. A prime number is a prime number on Earth and in the Andromeda galaxy. The value of pi doesn't change. So the idea is to build a message from the ground up using universal concepts. Start by establishing counting, then basic arithmetic, then chemistry and physics, slowly bootstrapping a shared vocabulary from first principles. Back in 1960, a mathematician named Hans Freudenthal even designed an entire artificial language for exactly this purpose, called Linkos, short for lingua cosmica, cosmic language, meant to be teachable from scratch using nothing but mathematical patterns. This is precisely why the Arecibo message led with prime numbers and simple counting. You have to teach the alien how to read before you can tell them anything. Whether it would actually work, nobody knows. But the bet is that any species capable of building a radio telescope must understand math. And that math is the one bridge that spans any gulf between minds. And yet, There's a humbling counter-argument that some thinkers raise, and it's worth taking seriously. What if an alien mind is so fundamentally different from ours that even math doesn't bridge the gap? We assume mathematics is universal, but the way we conceptualize it is deeply shaped by human brains, human senses, human evolution. A species that experiences the world through, say, electric fields or chemical gradients rather than vision and sound might carve up reality in ways we can't imagine. They might not see individual objects the way we do, or think in discrete symbols, or perceive time the same way. Their obvious starting point for a message might be utterly alien to ours. Some philosophers argue that true communication requires shared concepts, and shared concepts require shared experience, which we'd have almost none of. It's possible we could detect a signal, recognize it as artificial, and still never decode a single word of it, the way you might recognize that whale song is communication without understanding any of it. This is the quiet terror beneath all contact attempts, that we might prove we are not alone and still be unable to say hello. The gap between minds might be unbridgeable even after the silence is broken. Now let's move beyond radio, because radio is just one color of light. And some scientists argue we've been looking in the wrong color all along. Enter optical SETI, the search for laser signals. Just a couple of years after radio SETI was proposed, physicists pointed out that a powerful laser could be an even better interstellar beacon. Here's the astonishing part. A sufficiently advanced civilization firing a laser in tight, brief pulses could create a flash that, for a few billionths of a second, outshines its entire host star as seen from across the galaxy. Imagine a lighthouse so bright that in an instant it eclipses the sun it orbits. A pulse like that, aimed our way, would be unmistakable. No star naturally does that. Lasers can also carry vastly more information than radio, packing more data into the beam. So today, there are dedicated optical SETI projects scanning the skies for these nanosecond flashes. Telescopes watching millions of stars, waiting for one impossibly brief, impossibly bright pulse of light that could only be artificial. We might not hear aliens. We might see them blink. And here's where the search gets really wild, because everything so far assumes aliens are deliberately trying to talk to us. But what if they're not? What if they're just living, building, doing? Engineering on a scale so vast that we could detect the byproducts, the cosmic equivalent of seeing a city's lights from space without anyone signaling you. These accidental fingerprints are called technosignatures, and the search for them is one of the most exciting frontiers. The most famous example is the Dyson sphere. Back in 1960, physicist Freeman Dyson reasoned that a sufficiently advanced civilization would crave more and more energy, and the biggest energy source around is their own star. So they might build an enormous structure, a swarm of solar collectors, or even a complete shell, surrounding their star to capture most of its light. And here's the clever bit. No structure is perfectly efficient. All that captured energy eventually gets re-radiated as waste heat in the infrared. So a star wrapped in a Dyson sphere would look strange, dimmed in visible light, but glowing oddly bright in infrared. Astronomers have actually searched telescope archives for stars with exactly this weird signature. There have even been candidates. A star nicknamed Tabby's star made headlines when it dimmed erratically and dramatically, by as much as 20%, in a way no normal star does, prompting wild speculation about an alien megastructure mid-construction. The leading explanation now is dust, not aliens, but the mystery lingers. Whole projects, like one named after the Greek god of the forge, now systematically hunt for Dyson sphere candidates across the galaxy. To make sense of why scientists hunt for things as colossal as a star-sized shell, it helps to know how they rank possible civilizations by raw power. In 1964, the Soviet astronomer Nikolai Kardashev proposed a scale based on one thing: how much energy a civilization can harness. A Type 1 civilization controls all the energy available on its home planet, roughly where humanity is slowly heading, but we're not even there yet. A Type 2 civilization harnesses the entire energy output of its star. That's the Dyson sphere builder. And a Type 3 civilization commands the energy of an entire galaxy, hundreds of billions of stars. The reason this matters for contact is profound. The more advanced a civilization, the bigger and more visible its technosignatures become. We might never spot a civilization at our own modest level. They'd be as quiet as we are. But a Type 2 or Type 3 civilization, reshaping stars and galaxies, would leave fingerprints potentially visible across cosmic distances. This is why some searches scan not just single stars, but entire other galaxies, looking for the telltale glow of a civilization that has begun to dim whole swaths of starlight and convert it to waste heat. We may not find our equals, but we might just spot a godlike civilization by the scale of its engineering. And Dyson spheres are just the start. Other technosignatures scientists hunt for include industrial pollution in a planet's atmosphere, certain artificial chemicals that could only come from factories, detectable when we analyze the light of distant worlds, or simply the leakage, the radio and TV broadcasts spilling off a planet by accident, exactly as our own signals leak off Earth. We could potentially catch a civilization not because it's talking to us, but because it's talking to itself loudly. Then there's perhaps the most science fiction idea of all, but one taken seriously by scientists. Physical probes already in our solar system. The reasoning goes like this. If radio messages take thousands of years to cross the galaxy and get a reply, a far smarter strategy for a patient civilization would be to send a robotic probe to interesting star systems, park it there, and have it wait, ready to make contact if and when a local species arises. Back in 1960, scientist Ronald Bracewell proposed exactly this, that the smartest way to communicate across the galaxy might be to send a physical messenger that lurks quietly until it detects us. Take it further, and you get the von Neumann probe, a self-replicating machine that arrives at a star system, mines raw materials, builds copies of itself, and sends those copies onward to other stars. A single such probe could, in theory, spread to every star in the galaxy in a cosmically short time. Which raises a chilling thought. If such probes are easy to build, the galaxy could already be full of them. Some scientists seriously suggest we should be searching our own solar system, the asteroid belt, the outer reaches, for these silent lurkers, ancient probes that might be watching and waiting. When the mysterious interstellar object Oumuamua passed through our solar system, a few scientists openly wondered, however unlikely, whether it could be artificial. Almost certainly it wasn't, but it forced the question, would we even recognize an alien probe if one drifted past? And now we reach the frontier, the truly futuristic, mostly theoretical methods that go beyond light entirely. Because radio and lasers, for all their speed, have a weakness. Signals fade, scatter, and get drowned in cosmic noise over vast distances. So scientists have speculated about exotic messengers that could do better. One candidate is the neutrino, a ghostly particle that barely interacts with matter at all. Neutrinos can pass straight through a planet, a star, almost anything without being stopped. A civilization that could generate and aim beams of neutrinos could send a signal that punches through obstacles no radio wave could survive, virtually unblockable. The catch is that the very property that makes neutrinos unstoppable, their refusal to interact, also makes them fiendishly hard to detect, requiring enormous detectors. But an advanced enough civilization might use them, and a few scientists argue we should watch for artificial neutrino signals too. Even more exotic, gravitational waves. These are ripples in the fabric of space-time itself, produced when massive objects accelerate violently. And we only first detected them in 2015 from colliding black holes. Some theorists have speculated that an immensely advanced civilization could engineer gravitational waves deliberately, perhaps even using a black hole as a kind of cosmic broadcasting machine, creating ripples in space-time that could carry a signal across the universe in a way nothing could block or fade. It's far beyond our technology, but the point of cataloging these ideas is that a civilization millions of years ahead of us might find them trivial. And one more beautiful idea, using stars as lenses. A star's gravity bends light passing near it, focusing it like a giant lens. And our own sun has a focal point far out in space where it could massively amplify a faint signal. Some scientists imagine a galaxy-spanning communication network that uses stars themselves as natural relay antennas, signals hopping from one stellar lens to the next. We could, in principle, send a probe to our sun's focal point, and turn our entire star into a telescope, or a telephone, of unimaginable power. So we have the full toolkit now, from a golden record to a gravitational wave. But all of this leads to one final, uncomfortable question. And it might be the most important one in the entire field. Not how to make contact, but whether we should be trying to in the first place. But to understand that debate, we have to sit with the strangest fact in all of this. The one that haunts every scientist in the field. It's called the Fermi paradox, and it's deceptively simple. Our galaxy is unfathomably old, over 13 billion years, and contains hundreds of billions of stars, a huge fraction of them with planets. If even a tiny sliver of those worlds produced life, and a tiny sliver of that became intelligent, the galaxy should have been colonized, or at least filled with signals, many times over by now. Even traveling slowly, a single determined civilization could spread across the entire galaxy in a few million years. A blink in cosmic time. So the physicist Enrico Fermi reportedly cut to the heart of it with one blunt question. Where is everybody? By all rights, the sky should be crowded with signals and probes. Instead, we hear nothing. This deafening quiet even has a name, the Great Silence. And the proposed explanations are a tour of hope and dread. Maybe life is just exceptionally rare, and we're among the very first, or the only, intelligence to arise. Maybe intelligence reliably destroys itself through war or environmental collapse before it can spread to the stars, meaning we're hearing silence because everyone burns out. Maybe advanced civilizations exist but have no interest in radio, having moved on to technologies we can't even detect, so we're listening on a dead channel. Maybe they're out there and deliberately leaving us alone. The so-called zoo hypothesis, in which we're a protected wilderness no one is allowed to disturb. Or, most chilling, maybe everyone is hiding on purpose, and silence is a survival strategy. That last possibility leads directly into the most heated argument in the field. Because here's the divide. Listening is safe. You can eavesdrop on the universe forever and reveal nothing about yourself. But actively shouting, deliberately broadcasting our location and existence to the cosmos, is irreversible. Once a powerful message leaves Earth, it travels outward forever, and you can never call it back. And some very serious people think that's a catastrophically bad idea. The physicist Stephen Hawking famously warned that announcing ourselves could be like the indigenous peoples of the Americas broadcasting a welcome to arriving colonizers, that an advanced alien civilization might not be friendly, and that revealing a young, vulnerable, resource-rich planet to the galaxy could invite disaster. This dark possibility even has a name borrowed from science fiction, the dark forest. The idea that the universe is silent precisely because every intelligent species has learned that the safest thing to do is stay quiet and hidden, like creatures in a forest full of unseen predators. On the other side stand those who say this fear is overblown, that any civilization capable of crossing interstellar distances to harm us could already detect the radio and TV signals we've been leaking for a century anyway, so hiding is futile. They argue that staying silent forever out of fear is its own kind of failure, a cosmic cowardice, and that reaching out is part of what it means to be a curious, hopeful species. Carl Sagan himself, the great champion of contact, nonetheless urged caution, suggesting that the newest, youngest civilization in the galaxy should perhaps listen quietly for a long time before shouting. This unresolved tension between the urge to reach out and the instinct to hide runs right through the heart of everything we've talked about. We've built the golden records and beamed the messages and pointed the dishes, and we still haven't agreed on whether we should be answering or even speaking at all. And suppose one day we do catch a real signal. What then? It turns out scientists have actually thought hard about this, and there's a kind of informal game plan for the most important day in human history. The first and hardest step would be verification, ruling out that it's interference, a satellite, a hoax, or a natural phenomenon, which, given how many false alarms litter SETI's history, could take days, weeks, or longer of independent telescopes confirming the same signal. There's broad agreement that a confirmed detection should be announced openly to the whole world, not hidden by any single government. The discovery would belong to all of humanity, But after that, the plan dissolves into open questions. Who, if anyone, speaks for Earth? Should we reply at all? And if so, who decides what we say? There is no world government, no agreed authority, no treaty with real teeth governing this. The leading guidelines explicitly urge that no response be sent without global consultation. But there's nothing actually stopping a single nation, company, or even a lone individual with a powerful transmitter from firing off a reply on humanity's behalf. The most consequential decision our species could ever face has, essentially, no one clearly in charge of it. We've spent 60 years figuring out how to detect a signal, and comparatively little figuring out what we'd do the morning after. So that's every way we know to try to talk to the universe. Messages etched in gold and flung into the dark. Radio shouts and patient radio listening. Mathematical languages built from prime numbers. Lasers brighter than suns. The search for alien megastructures and industrial haze. Silent probes that might already be hiding among the asteroids. And the far future dreams of neutrinos, gravitational waves, and stars turned into telephones. 65 years of effort. Every dish we've pointed, every message we've sent, every clever idea for bridging the void. And the universe, so far, has answered with nothing but silence, which is itself a message. We just don't yet know what it means. Either we are alone, which is terrifying, or we are not, and everyone else is hiding, which is more terrifying still. Somewhere out there, the bottle is still drifting. The dishes are still listening. And the heartbeat we recorded in 1977 is still flying outward through the dark, getting farther every second, waiting for an ear that may never come.